If quantum mechanics hasn't profoundly shocked you, then you haven't understood it yet. Now, this is a statement by Nobel Prize winner Niels Bohr. It really resonates with me now that I've spent time learning and thinking about what quantum computing can achieve. Now, after my 10 minutes up, I hope you will feel the same. To give you a small teaser of what's to come, we're all extremely familiar with the COVID-19 vaccine. And I've got to say, I'm certainly invested in how it's going to bring back a return to normality. But even with immense effort and almost unlimited resources, it took more than a year. Take a moment and really consider what the impact of that year was. Now consider how the world would be changed if the vaccine had been in place after maybe a few months or even weeks. This is potentially the world that quantum brings about. So to the question, are we living in a post-digital world? What is the post-digital world? You're going to hear definitions today talking about being the world in which digital is a completely embedded standard or something similar. And they're going to be well thought through. But my view is we need a structural element to define the transition. So the building block of the digital age has been the bit. It's a 1 or a 0. It's the basis for all the computing we take for granted, and it's allowed the creation of our digital world. Now I propose to draw the new line to the post-digital based on the qubit, which provides the same backbone for quantum computing, in which I'll describe its role in a moment. So before I talk about quantum computing and what it can do for COVID-like outbreaks, I'm really going to reiterate the stakes we're facing. Take a moment, consider the profound shock that COVID-19 impacted on the world. The scale's immense. There's 2 million people dead, millions more with long-term health complications. There are massive mental health, educational and economic effects that we can easily overlook and say, well, things are going to get better. But consider that these are going to define many people's entire lives. Now for me, the pandemic has been the most important world event in my lifetime, and I really can't imagine talking about anything else currently. We've all been personally impacted in some way, small or large, and it's hard to think of a similar kind of shared experience. Now, throughout the year I've been lucky. Even at the very peak of the lockdown, my girlfriend and I have managed not to run out of toilet roll, perhaps more importantly wine. But I'm not sure I can force myself to another fun COVID round for a Zoom quiz. However, on a really serious note, I've had family, friends and colleagues that have tested positive, and some with health implications that might be long term. So it really emphasises to me that COVID is the thing that I have to talk about. Now, the most viscerally frightening thing about this pandemic is there's another to follow it, and most likely soon. Just consider what that would mean. Do you think we'd cope? Because I'm really not very sure. Now, human impact in the natural world has led from a transfer of diseases from animals to humans, and this combined with our completely interconnected world means that pandemics will be an ever-present issue for us unless we take some fairly major steps. And this is why I'm talking about quantum computing. It's uniquely placed to offer multiple answers to the hard questions we're being asked by COVID-19 and future pandemics, and on diverse subjects from drug development, logistics to even data security. Now, I'm going to give you a quick introduction to quantum computing because I think knowing the basics, it helps make it just that much more tangible. At least it does for me. Now, quantum computers transmit information via quantum bits. These are known as qubits. Sounds all very similar to a standard binary computer. And yeah, like the bit, qubits can exist either as a 1 or a 0. But the powerful difference is also both simultaneously. And it's this difference that gives quantum computers the potential to be exponentially faster than today's supercomputers, with the ability to do multiple calculations with multiple inputs simultaneously. Now I'm going to try and explain this with a simple example. Take a coin. If you flip it, it can be either heads or tails. But if you spin it, and hopefully this is spinning, it's got a chance of landing on heads and a chance of landing on tails. But until you measure it by stopping the coin, it can be either. Superpositions like that spinning coin, it allows for uncertainty. Now the second important property that differentiates quantum computing is entanglement. And this means that the qubits are linked. Changing one changes another instantaneously and in a predictable way. Now how or why entanglement works even baffled Einstein, who memorably described it as spooky action at a distance. But it's key to the power of quantum computers. In a conventional computer, doubling the number of bits doubles its processing power. But thanks to entanglement, adding an extra qubit, it provides an exponential increase in power, and I'll really come back to why that's important in a moment. So I want to give you an idea of what current quantum computers look like. If you look at the picture, you see just how complex they are at this early stage. Now, much of this complexity is due to quantum computers being really sensitive to noise and environmental effects, and it means the information being looked at only remains quantum for so long. And this is where many of the technical challenges currently lie, and it means that we need highly specialised cooled conditions. It's a big part of the reason why we just don't have practical quantum computing already. Now, after that whistle-stop tour to the background of quantum computing, I know it can be confusing, and I want you to remember this quote. If you think you understand quantum mechanics, you don't understand quantum mechanics. Now, even Nobel Prize-winning physicists understood it's more than a little complex, so don't get too caught in the detail right now. If you're interested, plenty of time at a later date. Now, given the enormous potential for quantum to change the way we model and the way we understand the world, the question I feel you want me to answer is, if it was in a more mature state, would it have helped us better prepare for a global pandemic such as COVID? And the answer is a categorical yes. There are many potential solutions that it offers. If you have a moment, looking at tools for optimization of resources, data security, and preventative technologies would be well worth your time. But right now, it's the area that tackles pandemics head on that I want to talk about, and that's drug and vaccine development. Now, some of you may be aware, but bringing a new pharmaceutical to market is both an imprecise and expensive process. Its timeline gives a view of how it can take a decade or more and cost billions without a guaranteed result. And this is a real problem when trying to react quickly to something that's a rapidly growing outbreak like COVID-19. Now, it took 12 days to map the spike protein of the COVID-19 virus you can see in this diagram. This is the part of the virus that attaches to and infects human cells, and it's been used as the basis for a number of the mRNA vaccines. In the 1980s, a similar analysis for HIV took 4 years, so presumably we're extremely quick right now. And I thought so, but unfortunately it's not really nearly enough, as it only takes us a small part of the way. If you want to know the properties of a molecule like this, and to predict its behaviour, you have to map them out. And an accurate understanding of this will allow us to screen databases for compounds that exhibit functions, such as we might look for like in a drug molecule that's able to attach to it and attack it. Now, this would greatly speed up the process of identifying a cure and really improve its efficiency. Now, I'm going to just bring up a couple of numbers because I want to hammer home the blunt message of why it really has to be quantum. To give you an idea why we can't just make current supercomputers faster, take modelling a relatively small molecule we've all heard of, like penicillin. It comes back to that bits versus qubits that I've tried to start everything with. To model penicillin, it's been estimated to require a supercomputer with 10 to the power of 86 bits. Now, this is a wildly huge number, but to put it in context, that's more than there are atoms in the observable universe. And while a quantum system would need a more achievable 286 quantum bits, so you can see why it needs to be quantum. Now, the molecule we're looking at, the spike protein, it contains many thousands of atoms. It's impossibly large for non-quantum computation now or ever. So just to make that emphasis, it needs to be quantum. Now, come to the way of working that could potentially change everything, which is end-to-end in silico drug discovery. Now, in silico just means via computer simulation, and it would mean transferring the entire drug discovery process into a quantum computer, bypassing potentially entirely the lab-based stage and allowing results to be obtained in fantastically short periods of time. In this case, such simulations would, with the appearance of a new epidemic, identify and develop a potential drug or vaccine in a matter of days or hours. It's not difficult to understand the impact the greatly shortened timescale would make. Now, after this leap, the bottleneck for drug development would move from drug discovery to human testing phases. Now, even these tests could potentially be expedited with the help of large-scale quantum computers capable of simulating the interaction of the drug and the humans right down to the molecular level. In this ideal world, again, simply look at the database of molecules, calculate accurately whether they'd serve safely as a cure, and we'd be ready to go. To be clear, this would change the entire direction of humanity. And it's with this potential that I'm going to come back to the initial question. So, to finally answer the question, are we living in a post-digital world? Now, I see mature quantum computing in the qubit as defining the transition from the digital age. So, my answer is we're at the beginning of the end. We're still in the digital age. We've got one toe in the post-digital, with world-changing applications just on the horizon. But before I leave you, I'm going to make a few asks to everyone in the audience. First, look at these technologies: cybersecurity, financial modelling, artificial intelligence. Now, realise that quantum computing could have as much of an impact in these areas as it could potentially for drug and vaccine development, and just think of the kind of revolution that'd bring. Second, leverage your positions. Quantum computing is already a field Atos is heavily involved in, and more investment means true quantum computing sooner, which will undoubtedly change the world. All that's left is for me to thank you for giving me your time. Thanks a lot.